In this video, I'll discuss solutions to challenge problem number 12, and later on I have a few interesting questions for you as challenge problem number 13. Now, I strongly suggest that before attempting these questions, go through your class notes, revise properly and give your best shot. Only then see the solution. This way you will get the maximum benefit out of this exercise. Remember, the objective of this entire exercise is to provide you more and more approaches for solving problems. Now, JEE Advanced is becoming tougher and tougher each year, and you will require different approaches for solving the problem. Having said that, let's start with solutions to challenge problem number 12. Let's start with question number 1. This is an interesting problem. Here we have to find out number of integers which satisfies this equation: m square plus m plus 1 whole square equal to n raised to the power 4 plus n plus 1 raised to the power 4. Let's expand it. This 1 and this 1 will get cancelled out, cancelling 2 on both sides. We will get something like this. Let's add 1 on both sides. Let's simplify the right side. I'll take n square out, so I'll get n square plus 2n plus 3 plus 2 by n plus 1 by n square. I notice that 2 by n and 2n are present here, and also I have n square and 1 by n square. In order to solve the right side, I can take n plus 1 by n as y. Therefore, n square plus 1 by n square will be y square minus 2. So if I simplify the right side, I'll get y square minus 2 plus 2 times y plus 3, which is y square plus 2y plus 1. This is a perfect square. Now replacing back the value of y, and if I simplify this, I take n square inside, so I'll get n square plus 1 plus n whole square. Equating left side and right side, we are getting m square plus m plus 1 is equal to n square plus 1 plus n whole square. Here m and n are integers. Now we notice that this is a perfect square, so the left side should also be a perfect square. Can we say that this is a perfect square? Let's check. We know that m square plus m plus 1 lies between m square and m square plus 2m plus 1. Since it lies between two immediate perfect squares, this cannot be a perfect square. Therefore, no solution is possible for non-zero integers. Now, since we have established that m square plus m plus 1 is not a perfect square, there is one remote possibility that m square plus m plus 1 can be equal to m square itself. There is an equality here. Or there is a possibility that m square plus m plus 1 is equal to m square plus 2m plus 1. Now this is a perfect square and this is also a perfect square. So this is the only possibility for m square plus m plus 1 to be a perfect square. If I solve it, m square gone, will get m equal to minus 1. Here if we solve it, we'll get m is equal to 0. So there are two possibilities where m is equal to minus 1 or m is equal to 0. If m is equal to minus 1, then if I substitute back into the original equation, which is, then if I put m equal to minus 1, we'll get here 1 is equal to n square plus n plus 1 whole square. If I solve it, then n square plus n plus 1 is either equal to 1 or minus 1. Therefore, n is equal to 0 or n is equal to minus 1. Whereas here when we solve, we'll get n square plus n plus 2 equal to 0. If I convert it using perfect square method, then I can write which for any integer is not possible. Therefore, solution from this case is m equal to minus 1, n equal to 0, m equal to minus 1, n equal to minus 1. These are the two possibilities. Case 2, when m is equal to 0. When m equal to 0, again when I substitute into the original equation, we'll get 1 is equal to this. So we'll get the same equation again. When we solve, again we'll get the same solution. So we'll get n equal to 0, n equal to minus 1. Therefore, two more solutions are there, m equal to 0, n equal to 0, and m equal to 0, n equal to minus 1. So these are the 4 different ordered pairs which are possible. So 4 solutions or 4 ordered pairs are possible. This is the answer. Next question is based on sequence and series. It's an interesting problem. If we try to directly solve it, then we will not get the answer. So we have to use some kind of trick, a different approach. Let's see what we can do. I'm going to replace m by n and n by m. So therefore, I will get n is tending towards 1 to infinity. Let's call this as equation 1. Let's call this as equation 2. Now, if I add both these equations, then I will get 2s is equal to, here the order doesn't matter, so I can write either ways. Inside the bracket, these both terms will get added up. Look at the denominator. We have this portion and this portion is exactly same, so I can take it common. Inside the bracket we have mn common. I can take that also as common outside. We will be left with this. If I take LCM, then we'll get something like this. These both terms will get cancelled and we'll be left with this part. Now we have a simplified expression. Finding out the value will be easy. Now we notice here that m and n are independent of each other, so therefore we can split this into two summations, both of which value will be remain same, because whether you take m or n, the limits are exactly same. Now let's find out the value of this. If I put m equal to 1, I will get this. If I put m equal to 2, I will get 3 square, 3 by 3 cube, and so on up to infinity. This is AGP. In AGP, we can multiply by the common ratio and write in the staggered form. Here I notice that the common ratio is 1 by 3. So therefore I divide by 3 like this, and I write 1 by 3 square. This term I am writing here. Similarly, this term I am writing here below this, and so on up to infinity. So when we subtract both these equations, we will get 2s dash by 3 is equal to 1 by 3 plus 1 by 3 square plus 1 by 3 cube, and so on up to infinity. The right side is a GP, infinite GP. The sum of infinite GP is a upon 1 minus r. So we can use that. So here we will get a upon 1 minus 1 by 3. So this will give us 1 by 2. So s dash is equal to 3 by 4. Let's put it back into equation 3. So 2s is equal to 3 by 4 square, which is 9 by 16. So s is equal to 9 by 32. That is the answer. Now let's look at question number 3. This is one of the best problems for JEE Advanced. So by looking at it, you cannot figure it out. What kind of series is this? Should we use binomial theorem or should we use some other series? Maybe, but the question can be solved using integration. Let's see how. Now we know that 0 to pi by 2 sine nx dx can be written as n minus 1, n minus 3, n minus 5, so on, divided by n minus 2, n minus 4, so on, and in the end pi by 2. This is the case when n is even. When n is odd, So this is the value of integration 0 to pi by 2 sine nx. Now depending on the value of n, you can find out different results. So let's just verify. Suppose I integrate 0 to pi by 2 sine x dx, then there will be only one term since n is equal to 1. So therefore the series will stop at 1 itself. So we will get 1 directly. You can solve it and see also. Integration of sine x is minus cos x. So if I put the limits 0 to pi by 2, I will get 0 and minus minus plus 1, right. So therefore 0 to pi by 2 sin x is 1. Similarly 0 to pi by 2 sin cube x, sin cube x will be, I substitute here, so 2 by 3 I will get, that is the answer. If I take 0 to pi by 2 sin 5x dx, then we will get 4, 2 in numerator, denominator will get 5, 3, 1. This is what we will get. Now let's look at the question. The question says fx is equal to x plus 2x cube by 1.3 plus 2.4 divided by 1.3.5. Now what we can do is, we can safely replace this entire thing by sin cube x integration 0 to pi by 2. Similarly, I can replace this entire thing by sin 5x 0 to pi by 2. So let's see what we get. So I will write fx is equal to 0 to pi by 2 sin x. Let's take sin t, new variable, and then we have x. Anyways, we have the next term x cube, and then in place of that fraction I am going to write sin cube t dt. Next term I am going to write 0 to pi by 2 sin 5t dt, and so on. The reason why I was able to do this, because there was a pattern. The numerators were all even numbers and denominators were all odd numbers. So that's why I could see that pattern, and then I replaced this with integration 0 to pi by 2 sin x. So therefore this will become 0 to pi by 2. I can combine them, x sin t plus x cube sin cube t plus x5 sin 5t, and so on. Now we notice that whatever is written in the bracket is again a GP with common ratio as x square sin square t. So applying the formula for infinite GP, I can write a upon 1 minus r. Now this can be integrated. I will write denominator sin square t as 1 minus cos square t, and I am going to substitute cos t as new variable u. Since cos t is u, differentiation of cos t is minus sin t dt will be du. Now the integration will change to minus du in the numerator, denominator 1 minus x square plus x square u square. This can be easily integrated. Integration limits can be managed. When t is tending towards 0, cos 0 is 1, and when t is tending towards pi by 2, cos pi by 2 is 0. So I can again change the limits and write 0 to 1, integration du upon 1 minus x square. Let's divide the entire thing by x square. Now we can directly integrate. This is tan inverse x format. So 1 by a tan inverse integration limits are from 0 to 1. So this and this will get cancelled out, and we will get tan inverse. In place of u, I am going to substitute 1. Tan 0 is 0. Therefore, this is our function fx. That's it, our work is done. So this is the final answer. Hope you found it interesting. Now let's look at challenge problem number 13. If you like the video, please like and subscribe the channel. I'll see you in the next video.